Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand tapestry of 17th century intellectual history, a period of breathtaking scientific and philosophical transformation, the threads of modern mathematics were woven not in the lecture halls of established universities but often in the quiet studies of dedicated amateurs. Among these luminaries, none shines with a more enigmatic and brilliant light than Pierre de Fermat, a jurist from Toulouse whose passion for pure thought reshaped the landscape of number theory and laid a foundational stone for the calculus. His method for finding maxima and minima, a technique conceived in the late 1620s and circulated through correspondence before its wider dissemination and eventual posthumous publication, represents a moment of profound conceptual breakthrough. Contained within its seemingly simple algebraic procedure is the very essence of differential analysis, an instrument of such power that it would unlock problems of tangency, motion, and optimization that had vexed thinkers since antiquity. This essay will explore the genesis, the mechanics, the immediate applications, the monumental legacy of Fermat's method, arguing that this contribution, despite its archaic language and logical ambiguities, is a crucial algebraic precursor to the calculus, a bridge connecting the geometric world of the ancients to the analytic framework of the modern. The problems of maxima and minima are as old as geometric reasoning itself. The legends of Queen Dido circumscribing the maximum possible area with a bull's hide, or the efforts of Greek geometers like Zenodorus to prove that a circle encloses the most area for a given perimeter, speak to an enduring human fascination with optimization. For centuries, these problems were approached with bespoke, purely geometric arguments of immense ingenuity. The masters of the Hellenistic period, particularly Apollonius of Perga in his work on conic sections, developed sophisticated techniques for constructing tangent lines, a problem intimately related to finding extrema. A tangent line, after all, can be conceptualized as a line that locally hugs a curve most closely, a geometric expression of a local maximum or minimum distance. The analytical tools of the Greeks, however, were constrained by their representational system. The reliance on diagrams and rhetorical description, for all its elegance, created a barrier to generalization. Each problem required a new, custom-tailored geometric proof, a virtuoso performance lacking a universal, repeatable algorithm. The intellectual ground began to shift dramatically with the work of François Viot at the close of the 16th century. Viot's monumental contribution was the creation of a true symbolic algebra, the ars analytica, or analytic art, by systematically using letters to represent both known quantities and unknown variables. He transformed algebra from a set of prescriptive rules for solving specific numerical problems into a powerful symbolic language for exploring the very structure of quantitative relationships. This innovation was the essential precondition for Fermat's work. Fermat, a deep student of Viot, saw in this new algebraic language a tool to achieve what he believed the ancient geometers like Pappus had possessed in their lost art of analysis, a method to work backward from a desired property to the conditions that produce it. Armed with Viot's algebra, Fermat could translate the geometric configurations of curves and tangents into the symbolic world of equations, where their properties could be manipulated and explored with unprecedented freedom and generality. His method for finding maxima and minima was born directly from this fusion of classical geometric problems with modern algebraic machinery. Fermat's procedure, which he called his methodus ad disquiendum maximam et minimam, is at once brilliantly insightful and, from a modern perspective, logically perilous. Its genius resides in an algebraic manipulation that prefigures the concept of the derivative. To comprehend its structure, let us consider a canonical problem Fermat himself might have tackled: to divide a line segment of a given length, let us say b, into two parts such that the rectangle formed by them, their product, is as large as possible, that one part of the segment be the unknown quantity a, the other part is therefore the quantity b minus a. The product to be maximized is the expression a times the quantity b minus a. Fermat's revolutionary step was to consider what happens to this expression at a point infinitesimally close to the maximum. He introduced a very small quantity, which he called e, and replaced it with the quantity a plus e. The new product becomes the quantity a plus e, multiplied by the quantity b minus the quantity a plus. He then invoked a concept he termed adiquality or ad qualitas. This was a nuanced idea, lacking the formal precision of the later limit concept, but it served a similar purpose. He posited that at a true maximum or minimum, the value of the function and the value at this infinitesimally displaced point are, for all practical purposes, equal. He thus set the new expression ad equal to the original one. So, at times the quantity b minus is ad equal to the quantity a plus e times the quantity b minus a minus e. Expanding the second expression algebraically yields a times b minus a squared minus a times e plus b times e minus a times e minus e squared. The initial expression a times b minus a squared is thus equal to a times b minus a squared plus b times e minus 2 times a times a minus e. The next steps reveal the method's core mechanism. Fermat subtracted the common terms from both sides, leaving 0 on one side. This results in the inequality b times e minus 2 times a times e minus e squared is equal to 0. Now comes the crucial and most controversial maneuver. Observing that every remaining term contains the small increment e, he divided the entire expression by e. This simplification yields b minus 2 times a minus e is equal to 0. At this stage, he has treated e as a non-zero quantity. The division by 0 is impermissible. In the final, decisive step, he suppressed or eliminated the term e, arguing that it was vanishingly small. This action is equivalent to setting e equal to 0. What remains is the pure condition for the maximum b minus 2 times equals 0, which reveals that a must be equal to b divided by 2. The line segment must be bisected, a result known to Euclid but now derived through a general, powerful algebraic algorithm. This procedure of introducing an increment, assuming its equality, simplifying, dividing by the increment, and then causing the increment to vanish, constitutes the algebraic heart of finding a derivative and setting it to 0. It was a technique that worked with astonishing reliability, yet rested on the seemingly contradictory act of treating e as both something and nothing. This logical sleight of hand would later provoke sharp critique, most famously from Bishop Berkeley, who derided such infinitesimal quantities as the ghosts of departed quantities. The utility of Fermat's method extended far beyond simple optimization puzzles. He quickly recognized its profound application to the classical problem of finding the tangent to a curve. He reconceptualized the tangent as the limiting position of a secant line that cuts the curve at two nearby points. By applying his method of inequality to the coordinates of these 2 points and then causing the distance between them, his increment e, to vanish, he could derive an expression for the subtangent. The subtangent is a line segment on the axis that, along with the point of tangency and its ordinate, defines the slope and position of the tangent line itself. This transformed the bespoke geometric constructions of the past into a systematic algebraic process. Any curve whose equation was known could now be subjected to this procedure to determine its tangent at any given point. Perhaps the most spectacular demonstration of the method's power came in the realm of physics, specifically in optics. The law of refraction, which describes how a ray of light bends when passing from one medium to another, like from air to water, was an object of intense scientific inquiry. While abroad, Snell had discovered the empirical relationship involving the signs of the angles of incidence and refraction in the early 1620s, but a theoretical explanation was lacking. Fermat, guided by a deep philosophical conviction in nature's economy, proposed his principle of least time. He postulated that light travels between 2 points along the path that takes the minimum amount of time. Since the speed of light is different in different media, this path is a straight line within each medium but bends at the interface. He formulated an expression for the total travel time as a function of the point where the light ray crosses the boundary. He then applied his method for finding minima to this expression. The result of this optimization, after performing the algebraic dance of inequality, was a derivation of the very law Snell had found through experiment. This was a triumphant moment. A purely mathematical tool, born from abstract considerations of algebra and geometry, had successfully explained a fundamental law of the physical world. It validated the power of variational principles in physics, a concept that would later become a cornerstone of mechanics in the hands of Lagrange and Hamilton. The intellectual lineage proceeding from Fermat's method is direct and clear, leading straight to the invention of the calculus by Isaac Newton and Gottfried Wilhelm Leibniz a few decades later. Fermat's work was known to the key figures of the era through the tireless correspondence managed by Marin Mersenne. Isaac Barrow, Newton's predecessor as the Lucasian Professor of Mathematics at Cambridge, developed a very similar differential triangle method for finding tangents, and his work was a significant influence on the young Newton. What Newton and Leibniz achieved was a grand synthesis and generalization. They took Fermat's ad hoc procedure and systematized it into a universal algorithm, the calculus, complete with a comprehensive set of rules for differentiation of various functions. The notation, particularly Leibniz's elegant dy dx, made the process mechanical and broadly applicable. Crucially, they also discovered the inverse relationship between the problem of tangents differentiation and the problem of areas integration, uniting them under the fundamental theorem of calculusa connection that Fermat, for all his genius, had. Nonetheless, the debt owed to the lawyer from Toulouse is immense. Newton's method of fluxions, which considers rates of change, and Leibniz's differential calculus, which manipulates infinitesimals, are both formalizations of the core dynamic idea present in Fermat's introduction and subsequent elimination of the increment e. Later mathematicians, looking back with the benefit of historical perspective, recognized Fermat's foundational role. Joseph Louis Lagrange, one of the great architects of analysis, explicitly identified Fermat's method as the true origin of the differential calculus, praising its algebraic purity before it became entangled with the confusing concepts of motion or indivisibles. The method's primary weakness, its lack of a rigorous logical foundation for the handling of the infinitesimal e, remained a persistent issue. The full resolution of this problem awaited the development of the formal theory of limits in the 19th century, with the epsilon delta definitions of Augustin Louis Cauchy and Karl Weierstrass, which finally provided a solid logical bedrock for the magnificent edifice of calculus. In conclusion, Pierre de Fermat's method for finding maxima and minima stands as a landmark of human intellect, a pivotal creation that irrevocably altered the course of mathematics, emerging from a fertile synthesis of ancient geometric problems and via its new symbolic algebra. It provided a general procedure for solving a class of problems previously tractable only by piecemeal geometric artifice. Through the ingenious, if logically precarious, device of equality, Fermat captured the algebraic essence of the derivative, applying it with stunning success to problems of optimization, tangency, and even fundamental physics. While it fell to Newton and Leibniz to construct the full, systematic architecture of the calculus, their work was erected upon the foundation that Fermat had laid. He was the great precursor, the prince of amateurs who, working from his provincial home, devised a tool of such astonishing power that it would become indispensable to the scientific revolution. His method serves as a timeless testament to the power of abstract thought to illuminate the world, demonstrating how a single, elegant idea can bridge epochs and pave a royal road for future generations of thinkers.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.